before we go to the dimensional data model, we have to discuss about what is a data model. So when we are talking about data modeling is basically a process of defining the data structure in the best possible way, so that the way we store the data in the storage, whether it is a file based or it is database, so we need to require a structure. So the best possible way basically is considered in two different ways. What kind of flexibility you are providing at the data modeling, means data design level, and what kind of performance it can provide. So suppose if you design a data structure which is very flexible, means whatever future requirement comes, it can accommodate without much changes at the application level or impacting them. But the performance is impacted very badly. So such data model will not be accepted by the users or user community. Secondly, if you are giving a very best performance, means data query, data manipulation is very fast or very quick. But whenever there is a small change at the user level and that has to be accommodated within the existing data structure, and there you find, okay, a lot of changes are required at the application level or reports level or query level, then that also will not be accepted by the user, because they have to incur a lot of time as well as cost to accommodate even a small change. So these two has to be balanced, means performance plus flexibility. So flexibility in the sense to scale the data structure in future. So these two things should be balanced when we go for a data modeling. That is why which data model approach we should use for designing the data structure, that matters a lot. So earlier, like before data warehouse, we had only one type of database. We used to refer as the OLTP database or transaction database or operational database. So these two different names were there. So since there was only one type of database, so we had one type of data model, like ER model. In between, some other models came, but they were not very successful, like hierarchical data modeling or object data modeling, but they were not successful with business data. So ER modeling was the most robust and it was used for a very long time. But when the data warehouse came into existence, so initially data warehouse was designed using the ER model. But it failed, means for initial 5-6 years, whatever data warehouse were designed, they started failing whenever the changes their requirement means required, or wherever the clients were trying to analyze the data in a different way and they needed more data or more data structure. So they find that, okay, because of this data model which we are using for data warehouse, extending the data warehouse in future for new requirements or to accommodate the new requirement is not very easy. It's taking a lot of time as well as cost also. So they started thinking, why not we develop a new data model so that can provide a flexibility. Means whenever new requirement comes, we should be able to accommodate them. So before they going for a new data model, they find out what is the problem with ER data model, means why we are not able to use the ER data model effectively with the data warehouse. So what they find is, since purpose of data warehouse is to extract the data and analyze, purpose of data warehouse is not to manipulate the data. All the manipulation of data is done at the OLTP level, means transaction level. So when they find that when we are using ER model for transaction database, the primary purpose there is to provide a better flexibility and performance at the transaction level. It means data manipulation level. Insert, update, delete should be fast. But whenever they are trying to query the data, performance becomes slow because those databases are very highly normalized. It means we avoid the duplicate data. Suppose if customer data is there, we keep only in one table and we don't duplicate the customer data in any other table. And there is some problem with the duplicate. Suppose if we keep customer data in 3 tables, whenever a new customer is added, we have to perform 3 operations at database level. Whenever we are updating the customer data, again we have to perform 3 operations. So one real life operation requires 3 database operations. So to avoid this, the best approach for transaction database was go for very highly normalized database where data redundancy is completely avoided or maximum avoided. So that data model was good for transaction, means data manipulation. But because of this normalization, what happens? So many tables are created in the database and those tables relation has been defined. So table A to B, B to C, C to D, like that. So the problem was data was very distributed. So it is like customer data is kept in one table, customers maybe family data is kept in another table, customer education data is kept in third table, customer, suppose if there is any financial data is kept in fourth table. So it is like based on the group of data for single entity, we have multiple tables. Now when we come to the data warehouse, we want to analyze the sales data based on the customer. So sometimes based on the customer personal data, sometimes family data, sometimes financial data. So if we keep multiple tables for a customer, then our query has to go for multi-join, and the many joins will degrade the query performance. So they find that, okay, this is the problem with the ER model, because number of tables are being created more, and because of that number of joins are happening more at the time of query. And when we do analysis of data, it is not possible that you analyze the data only using one approach, means just a customer-wise sales data. That is not possible. So most of the time we go for a multiple approach or multiple angle, like customer-wise, city-wise, what is the sales data, customer-wise, city-wise, maybe like branch-wise, what is the sales happening. So it is like we have to take multiple entities to analyze single maybe sales data or dispatch data or payment. So it was like when we are going for analysis, we have to use 7 tables, 8 tables, 15 tables, and because of that performance was getting degraded. So they came with this another data modeling. So they try to introduce, or they introduce dimensional modeling, where they reduce the number of tables. So what they say, let us keep only one table for one entity. Suppose if entity is a customer, we will have only one table for customer data. So whether it is his personal data or family data, so we try to club them in single table. But when we are clubbing these data, there is a chance that some of the data will repeat. So suppose if a customer has 3 addresses, so it means the customer personal data is going to repeat 3 times, because we are keeping 3 addresses. So in the data warehouse, we follow this approach. And that is why it is referred as a data warehouse is a very highly denormalized data, because duplicate data are very common, are happening very frequent. But the advantage what we get from this approach is since number of tables are reduced at the time of query, joins are reduced, so performance becomes very fast. So the dimensional model, when it was introduced, it became very popular because number of tables are reduced. But duplicate data is there. So it is like if OLTP's database size is 1 GB, and then we take the same data as it is in data warehouse, because of this duplicate it becomes 2 GB or 3 GB, means double or triple, because data is repeating multiple times. But the purpose of data warehouse was only query and analysis, so it was not a problem. So that is why this dimensional modeling gradually it became very popular, because of the performance it provides as well as flexibility. So one more thing what they adopted in the dimensional modeling is, when we reduce the number of joins among the tables, so naturally it is like whenever you are introducing some new table, it is not going to impact many tables. It might impact 1 or 2 relations, but not 4, 5 or many relations. So that also was provided by this dimensional model. So it was like introducing any new entity in the form of table does not impact many tables existing or application. So these two purposes were the main. First was performance should be better by reducing the number of tables and joins, and second was don't relate tables unnecessarily with each other, like circular approach. Better you keep them isolated. So they introduce under dimensional modeling, they introduce different submodels. So one of them was a star schema model, other was a star flake, then a snowflake. So they came with so many, means it was like gradual progression was there. Means when they came back to this a good dimensional model. So under dimensional model also we have 4 or 5 submodels, and out of those 4 or 5 submodels, the best model is referred as a star schema model. So we'll discuss that what is the main advantage of a star schema. So gradually they came to the star schema. So it was not like the very first time they introduced the star schema. So they came with ER model to dimensional model. So the basic difference between the ER model and dimensional model is, in ER model, we are dealing with so many tables which are related to each other in the very circular way or relational way. But in the dimensional model, they try to avoid this circular kind of relation, and they try to keep isolated relation among the tables. It means like if I have 10 tables, so let these 10 tables be related with each other, not directly, through one common table. So it was like all these 10 tables are related to each other through one single common table. So there is no direct relation between table A and B, B and C, C and D. It is like there is a table Z, Z table is going to sit between all these tables. So A to Z, B to Z, C to Z, like that. So suppose I want to access data from A and B table, I need to use the Z table. So A to Z and then Z to B, you will be able to relate. So this kind of approach was introduced, which was referred as the star schema. Later we'll discuss why this star name is given, why not any other name. So when we are talking about this, data modeling is the process of defining the structure. So as I discussed, like we are dealing with two different database. One is the OLTP database, which we are using right from the beginning. As soon as any organization comes into existence nowadays, they come with their OLTP database, which is to capture operational data. Means whatever events are happening in the organization, their details will be captured in one database, and that we refer as the OLTP. But the second part of the company is means they have to grow. So like if you see in any company, we have two types of employees. One type of employee we refer as the staff, and the second type of employee we refer as the management. So if you closely watch the staff and management, what is the difference? All the physical activities related to events are done by the staff. Like you take the example of bank. Within the bank, we have a deposit, one activity, withdrawal, another activity. Some people come for demand of means or check deposit. So the people who are involved with these activities or process, we refer them as the staff. But you will find one or two persons are in the bank branch who are sitting in a room where we written manager. And that person is not involved with day-to-day activity. So what he does, so people say he does manage. The question is, what is the management? Means whole day he is sitting in the room. So what is the management? So basically he gathers day-to-day information and he will analyze what is the business today. So today deposit has come maybe 10 million rupees or $1 million or $10 million. So he will analyze, okay, in this week total deposit is $10 million. Withdrawal is $0.8 million. What was the earlier week? The earlier week was $15 million and it was like $10 million were withdrawn. So he has to analyze why these differences are coming. One week deposit is very good, other week is very bad or very poor. So he will cross-check with multi-year data. Means, okay, in the month of January deposit is more every year, but in the month of February deposit is less. So he will see why this is there. So if it is India, will people say, okay, deposit is more in month of January and February because financial year is coming. So people try to go for FD and all those. Means March, they have to go for tax saving. So January, February, March, they will deposit for tax saving purpose. But as soon as March is over, April, May, June, people will start either withdrawing the money or they will not deposit that much which they have done in first 3 months. So these kind of analysis they do. So what is the advantage of this kind of analysis? These the managers they say, okay, so next year when the January is about to start, we will be ready with proper campaigning, proper offer, so that more and more people we can attract for deposit, so that our bank business will grow. And this is not only bank, any business they analyze which month is the festival, how to prepare our business for that festival so that we can sell more and more products. Maybe we give more discount, but we sell more so that we make more profit. So percentage-wise profit may be down, but absolute value-wise profit might be good. So that kind of thing is possible when you analyze the data from the past. And that is where data warehouse came into existence. So when it comes to OLTP, so OLTP is like, it keeps only 1 year data or maybe 6 months data. But data warehouse says that if you analyze only 6 months or 1 year data, that will not be enough because you have to capture the different patterns which are happening year-wise or month-wise or quarter-wise. And that can be done when you capture at least, in worst case, 5 years. But generally companies, they say 5 years is not good enough. We have to go for 10 years, 20 years, 30 years. That depends upon the life cycle of the product. So suppose we are dealing with the consumer product like grocery product, they say 3 to 5 years is good. But when you are dealing with other products like refrigerator or fridge or TV, where people don't change these products every year or every month or every quarter, they might change once in 3 years or 5 years. Then life of those products will be like, we have to analyze 3 life cycle. It means 10 years or 15 years. So this, when we go for data modeling, how we design OLTP data for only current data, how we design data warehouse where we have to keep historical data for very long duration. So that is why 2 different models came. your OLTP and ETL, OLTP and data warehouse. So ER modeling and dimension modeling. So this, when we are going for data modeling, whether you are learning ER modeling or you are learning dimension modeling, we have to be very sure why we are learning ER modeling, why we are learning dimension modeling, what is the difference in these two models. And especially the people who are targeting a data warehouse or BI, they have to know the ER modeling also. The reason is, when we say that, okay, dimension modeling is good, dimension modeling is flexible, dimension modeling is good. So it happens like, okay, you are saying that this model is good. So tell me, what is the problem with the other model, which has been used earlier but not being used? And if you never know about that, then you cannot explain, and you cannot make users or your client satisfied or justified. So that is why, even though if you are not doing ER modeling, but the basics of ER modeling you need to upgrade, so that you can do the comparative analysis and you can put it in front of client. See, why we are using dimensional modeling for data warehouse, your data warehouse, and why not ER modeling? This is the reason. So now in this slide you can see there are three different data models out there. ER modeling, which we have already seen, it is for OLTP database. Dimensional modeling is for data warehouse. And now the third one, which has come very recently, about 2 years back, they have published a white paper, and gradually it is picking up in the market. That is a data vault modeling. Data vault modeling provides complete flexibility to design the data structure. So it means with ER modeling there is some restriction, means there is some problem. It is not very flexible. So at one point you have to make a lot of changes to accommodate the new requirement. So that problem was taken care by dimensional model. So dimensional model provides better flexibility to structure the database or structure the data storage. But still, dimensional model has one problem, means there was a flexibility with dimension, but when we talk about the fact table, there is a type of data which we keep. Fact table has a flexibility problem. So then this data vault modeling is introduced, and data vault modeling has taken care of even that restriction also. So with the help of data vault modeling, we can design our data warehouse in a very flexible way. That means whatever structure is designed today, in tomorrow if your business is changing drastically and you need to accommodate them, still your data vault model says that nothing has to be changed at the existing level, only you have to just introduce the new things. And that is the biggest advantage of data vault modeling. But the problem is, the more flexibility any model provides, it is a bit more complex. Means technically it is a bit more complex. And that is the reason why data vault modeling is still not very popular, or is not capturing the market in a very fast way, because it is very technical and it's not possible that you can introduce the way we introduce the dimensional model. So anyway, data vault modeling is out of our scope, so we'll discuss about dimensional model. So when we go for modeling, we have three different type of model which we have to prepare: conceptual model, logical model, and physical model. So whether you are working with the ER modeling, or you are working with dimensional modeling or data vault modeling, you have to prepare three different documents: conceptual, logical, and physical. Conceptual model and logical model are prepared for the user to make them understand what the data modeler has understood about their requirements. So this is basically a method where data modeler try to make sure that whatever understanding I got from the user regarding the requirement, whether those requirements are properly captured and understood or not. So for that purpose, we prepare conceptual model and logical model, and no technical term will be used in these two models. But based on this these two models, once we get the complete understanding, then we are going to define a physical model, and that is basically a technical model. And the technical model is not shared with the client, because they might not understand until they themselves are technical, or they have a technical guide to analyze these physical model or technical model. So these three models, means different documents are prepared: conceptual, logical, and physical. So in very brief, I will tell like what is in conceptual. So in conceptual model, basically we try to show them what are the objects and what are the process, how they are related, that we try to show them. So subjects are objects, they are referred as an entity in ER model, and they are referred as a dimension in dimensional model. When it comes to process-based things in ER model again are referred as an entity, but there we say transaction entity and master entity. So whatever things are subject and object based, they are mastered in ER modeling, and process based entities are referred as a transaction entity in the ER modeling. But the same two things when we come to the dimension modeling, subject based entity we refer them as a dimension, and process based things we refer as a fact. So when we go in detail, we'll discuss what is a dimension and fact, because that is the core of dimension modeling. So in the conceptual model, we don't discuss at the attribute level, or we don't discuss at the business rule. We just discuss about what are the entities are there and how they are related, or what are the objects are there and how they are related with the process. So once conceptual model is approved by the user that okay, whatever you captured is perfect, then we go and introduce attributes level. Means under each entity, whatever attributes are required, we list out. And if suppose there are some business rule defined on those attributes or the relation, that also we mention. And then again we go back to the user and say that now let us check. Customer is one entity and these 40 attributes I got. So if these 40 attributes are enough, or do you have anything else which I missed? So attribute level, and then sometimes they have some rule like customer name must start with alphabet, or salary cannot be less than 5,000 for this job, or less than 10,000 for this job. So these kind of things we refer as a business rule, or you can say in database term as a database constraint. So these things are mentioned in the logical model. So basically your conceptual model is expanded in the terms of attributes and business model, and that is the logical model. So once that is approved, it means entire input is whatever is required for data model, physical data model is gathered. Now we can start the physical model. So whatever way we define the things in conceptual model and logical model, there will be a lot of changes when we go for physical model. So they won't do exactly the same way. So it is like in conceptual model we might show customer as one entity, but in the physical database customer might become 4 tables or 5 tables. So that kind of changes will be there. So the same thing basically in these slides are mentioned, like what is a conceptual model, what is logical model, what we require. So these things I'm just bypassing. So we will go to this dimensional model, and this dimensional model is basically based on our real life structure, which we refer as a cube. Like in real life, whenever we say cubical object, or this is a cube based. So basically, cube generally we refer as a three-dimensional object. Like suppose if we have take example of water tank, which is a cubical structure. So when we say it is a three-dimensional object, it means there are three different angles to this object. So when we say water tank, I am talking about rectangular water tank, not the circular one. So in case of rectangular water tank, we have three angles. One is the length, other is the width, and third is the height. So it may be like the water tank is 10 by 10 by 10, means 10 feet by 10 feet by 10 feet. And because of these three angles, whatever shape has come, it can accommodate maybe maybe 10,000 liter of water. 10 by 10 by 10, 10,000. So if I want to increase the water storage capacity of the tank, so we have a three different angles to play with. Means we can increase the length so that it can accommodate more water, or you can increase the width, or maybe height, or maybe any combination. So you can go for increase a little bit of length and little bit of width so that you can accommodate 2,000 liter water more, or maybe all the three. So when we are talking about this dimensional structure, it means we are trying to define something where one thing is at the core, means core level, which is surrounded by multiple objects, and each object is going to impact this central one. So the dimensional model theme is your data which you want to analyze, keep in the middle. And what are the different angles to view the data or analyze the data, keep them surrounded. Means surround this data from different angles. So those angle data or angular data we refer as a dimension, and whatever data is kept in the middle for analysis, that is referred as a measures or fact. So within the dimensional model, these two words are very common, dimensions and fact. Fact is a data which is analyzed, and dimension is nothing but a different angle to analyze this data. So it is like suppose if we want to analyze the sales data. So there can be different angles like customer-wise sales, branch-wise sales, city-wise sales, product-wise sales, or it may be like I want to go for combination, means customer-wise, product-wise, what is my sales, or branch-wise, product-wise, what is the sales, or customer-wise, product-wise, branch-wise, what is the sales. So different permutation and combination is possible with the dimension. But what is going to be analyzed? That is your fact data, which is kept in the middle. Since it is like I'm talking about water tank. So what is the core data? It is water. Means water storage or storage capacity, you can say. But this storage capacity depends upon three different angles: length, width, and height. So storage capacity itself is nothing. If you reduce any of the dimension, storage capacity will get impacted. So that is the core theme of the dimensional model. So since this cube object or three-dimensional object, we are very much familiar in our real life. You can say most of the people, they are familiar with. So when they come to the dimensional model, for them understanding this dimensional structure, which is the cubical structure, is not a very tough job. It is very simple. The only difference between a real life cube and the dimensional cube is data warehouse cube is real life cube we refer as a three-dimensional, but when it comes to data warehouse dimensional model structure, we refer it as a multi-dimensional. It means there can be more than three cubes also, or there can be less than three. So maybe only two dimensions are there. That is also a cube, or it can be 5 or 6 dimensions. So that also will be a cube. So it is referred as a multi-dimensional object. But when we introduce, when we go in the practical, we use this cube term very frequently. So we say that, okay, let us create one cube for sales process, one cube for purchase process, one cube for payment process. So it means we are talking about multi-dimensional structure where fact and dimension both are combined together. Like this is one example of, you can see this picture where fact is in the middle, and then we have a product as a dimension, customer, time, and data. So 4 dimensions are there. But this type of structure we refer as a star schema. So it means earlier we have discussed the dimensional model has a different type of submodel. One of the most popular submodel is the star schema model. So it is like when we design our data warehouse, about 90% of the time our data warehouse are designed based on a star schema. In very rare case we go for other model which we refer as a hierarchical approach like Snowflake or Snowflake. And that is the reason why some people they get confused that dimensional model and star schema model both are same. Basically, star schema model is one of the model under dimensional approach. So it is like a dimensional model is a higher level, which is a group of model, and star schema is one of the model which is most popular model. And the basic theme of star schema model is keep your data which you want to analyze in the middle, which we refer as a fact. And whatever are the different angles to analyze this data, we refer them as a dimension. So they should be kept separately, but connected to this fact table. And the third point which is important is whatever dimensional data are there, they should not have any relation with each other. It means no relation with dimension to dimension. All the dimension data should be related to the fact data only. So that is the basic theme of star schema model. So the question comes, why we are saying this as a star? So one of the reason, like people say, if you design a structure for this relation, means you take dimension, you take fact in the middle, and if you draw a diagram, it looks like a star. So some people they refer like this, but the actual thing is not this diagram. Actually, it is taken from our real life example of solar system. Like we are part of one solar system where sun is a star, and then different planets are there, like Earth is there, Mars is there, Venus is there, Jupiter is there, so many planets are there. So if you see this, this is referred as one solar system, where one star is there and multiple planets. And all, all these planets are related to the star, but there is no dependency between one planet and another planet. So it is like if one of the planets gets damaged, it does not impact the other planet. So this star schema model basically is derived from our real life example of solar system. So the way our solar system is there, one star with multiple planets, which is referred as a dimension. Exactly same way this star schema model is there. So because in the solar system, the star is the core. So without a star, there is no importance of planet, or there is no existence of planet. That is why this is referred as a star schema model. So that is the base reason why name is given a star schema. It is not like because the picture becomes like a star. So we have to discuss about when we are talking about dimensional model, two basic types of data are there: dimension data and fact data. So what is the fact data? So the generic definition of fact is like if you open a dictionary, English dictionary, and you see the definition of fact, it says that any truth is a fact. It means customer name, that is one truth. It is a fact. Date of birth, that is a fact. Gender is a fact. So any attribute which is basically a truth about an entity. So that is a dictionary meaning. But when it comes to dimensional model, fact meaning has been restricted. So it says that any attribute which is a numeric or any data which is numeric and it can be used in mathematical operation is a fact. What they say that don't take every attribute as a fact in the dimensional model. Only the numeric attribute should be fact, and every numeric attribute also is not a fact if they cannot be used in mathematical operations. So suppose say pin number, or you say maybe like a phone number. So we know that phone numbers are all numeric, but the problem is those numeric values are not useful for mathematical operations. So that we don't refer as a fact. And because of this, again there is a conflict. Like some people say that you are changing the basic meaning of this fact word. So due to this, some people we started using instead of fact, we say let us use the word measure, because measure gives more meaning. Measure means any attribute which can be used for the measurement. So measurement means, like suppose if I say sales, sales quantity. So with the help of sales quantity, I can measure the performance of customer. So which customer has purchased more quantity, he is the best customer. Which customer has purchased least quantity, he is the worst customer. So it means we are trying to analyze the customer who is good for our business and who is not good. So that is referred as evaluating the performance of different dimensions using the fact. So whether you say facts or measure, basically both are same. So fact, like some people they have a reservation that no, fact meaning is not correct in your dimensional modeling. So okay, in that case we say let us go for measure. So these facts are these measures wherever you keep in the database. So database means a table. So the table which you take to keep these measures or facts, that is referred as a fact table. So facts are nothing but attributes which are numeric, can be used in mathematical operation, and the fact table is the table where these facts are maintained. And since we have seen in the star schema model, the fact table should be in the middle, surrounded by the dimension. So it means within the fact table, there will be some other column which are referred as a foreign key. So all the dimension tables are like a parent table for fact table. So it means primary key of the dimension table goes to the fact table to establish the association. Then comes the dimension table. So what type of data should be in the dimension table? So answer is like whatever data is required to analyze those facts, we refer them as a dimension. And dimension data are mostly subject based, like customer, product, branch, country, city, state. All these are referred as a subject. Why we refer them as a subject? Because they are responsible to initiate the process. So when we say sales, sales cannot happen by its own. Sales happens only when some customer comes, some products are available. If suppose you remove a customer and remove a product, there is no sales. So subjects are those things which initiate the process, and processes are nothing but activity. So any activity will happen when at least one subject is involved. So in the data warehouse and dimensional modeling terms, subjects are referred as a dimension because they are responsible to initiate the process, and facts are basically process based where we keep the data which is analyzed by different subjects. In the star schema, dimension tables are the parent table and fact tables are the child table. So whenever we are going to establish the relation between dimension and fact table, it is like primary key of the dimension table should go to the fact table as a foreign key to establish the relation. And this dimension table with one fact table, that structure is referred as a cube. So that is a cubical structure or multi-dimensional structure. Now when it comes to subject data and process data, so one thing should be very clear. In any business, where will be the maximum data? So answer is whatever are the process data, they will be maximum. Because suppose you take example of bank. It may be possible that one bank has only 10,000 customers. But these 10,000 customers might be generating 1 lakh or 2 lakhs or 50,000 transactions per day. So in one day, we are getting 50,000 records in the transaction table, but the customer table is only 10,000 records. So if you consider 100 days transaction, it is like 50,000 into 100. So it becomes like 50 lakh records in the transaction table, but your customer is only 10,000 records. So when we are talking about this data volume between dimension and fact table, so it is like if you are maintaining 5 years or more data within your cube, means fact and dimension table. So it is like about 90 to 95% of the data will be within the fact table, and just between 5 to 10% data will be with the dimension table. Because dimension data are master data which are not changing or increasing very fast. But the transaction is happening very fast, means within an hour there may be millions of transactions. Like you see the Facebook, they have 1 billion means users are there, and these 1 billion users, they generate like 10-15 billion transactions per day, or it is more. So even though their dimensions are having a very good number of data like 1 billion, but the kind of transaction they generate is like 10 times 10 billion or 50 billion like that. The transaction data is always very high. So in the case of fact table, you will have a very huge amount of data, but number of columns in the fact tables are very less. Like suppose 10 dimensions are attached, 10 foreign key column, and maybe we are keeping another 10 measures like quantity, rate, discount type of column. So total number of columns might be only 20, but the number of records may be million, 10 million, 100 million, 1000 million, or billion. When it comes to dimension table, number of columns will be very high. Like customer may have a 200 columns data or 300, but the number of records may be some 100, some 1000. In a very rare case, they go in millions and billions. So this is how the data is distributed among dimension and fact table, and how the columns are structured. So this is one sample of a fact table. Like the first 3 columns, product code, account code, day code, these are the 3 foreign key columns from their respective dimension table. And the last 3 like unit sold, revenue, profit, these are the measures. So unit sold is nothing but quantity, revenue is nothing but amount, profit is nothing but amount. It may be amount or it may be percentage. It depends how the user wants, or user wants both. So generally this is the structure of a fact table, two types of columns, foreign key columns and measures or fact columns. And we have discussed like a dimension. Dimension basically represents object. There is a rare case where a dimension might be based on a process also. Sometimes it is possible that sales process is a fact table and the sales process is also defined as a dimension table. But that possibility is rare, but it is possible. So whenever we say that dimensions are always based on subject, basically that statement is not 100% correct, because sometimes dimensions might be based on even a process also. So there is a certain case that we will discuss later. But as I said, like 95% of the time, your dimensions are based on subject, not on the process. So like when we are talking about dimension model, we have these 3 different type of submodel: star model, snowflake, and multi-star. And there is like there is a small variation of star model that we refer as the extended star model. So most of the people, they say that there is no need to deal these two as a 2 separate model. Within star itself, we can consider as the extended also. And then snowflake also has one variation which we refer as the starflake. So the difference between starflake and snowflake is a hierarchy. If a dimension has a single hierarchy, we say starflake. But if the dimension has a multiple hierarchy, then we say snowflake. So that is the only difference. So that is why some people say that when you are talking about snowflake, you are talking about the hierarchy. So there is no point of discussing on the starflake. So basically they say remove starflake, because snowflake includes starflake itself. So some people, they do not agree that okay, starflake is a data model. They say snowflake is good enough. So that is not a point. There is no need to discuss or fight on this point. No, starflake is there, snowflake is separate. Basically snowflake includes starflake. And the third one is a multi-star model. Means it is like when you are designing your data structure based on a star model. So you are designing a cube, and it is very rare that your entire data warehouse or entire data mart will be completed with single cube. You will require multiple cube. It means you will require multiple fact tables, or you can say multiple star schema based cube. So when you are designing more than one cube for your data warehouse or data mart, then it becomes multi-star. So there is nothing very specific in case of multi-star or galaxy model. Basically it is like when you design 2 or more cubes based on a star schema, you say multi-star model. If you design 2 or more cubes based on a snowflake schema, then you say multi-snowflake model. So but why we need to discuss this multi-star model or galaxy model separately? Because whenever you design 2 cubes, there will be some common dimension between those. So those common dimensions we refer as the conforming dimension. And basically they are like a bridge between 2 fact tables. It means I have a sales fact table for sales data, and there is a payment fact table for payment data. And we know that whenever we are doing the analysis of sales, we require payment also. Means we would like to know how many sales are done where payment is 100% received and how many sales are where payment is partially received. So it means within the report, analytical report, we have to show the total sales amount as well as total payment amount received. But the problem is these two data are kept in two separate fact tables. And fact table to fact table, there is no relation. Means in dimensional model, it is very clear. Don't relate one fact table with another fact table directly. Then question is how? So answer is you have to go through the dimension. It is like suppose we have a customer dimension between sales and payment. So whenever you want to connect sales data with payment data, we have to use the customer, which is the common dimension. So some people refer it as a bridge dimension, some people say it is like a link dimension, but the proper word is the confirming dimension. It means this is a dimension which is confirming the relation between two cubes or you say two factors. So for that purpose, we have to discuss this multi-star model also. So out of these means, as we have discussed, the best model is a star model, or then you say multi-star model, because multi comes by default. When you keep on designing your cube using a star model, multi is by default. So there is no extra effort or there is no extra point which we have to learn or apply for multi-star. So here we talk about when we talk about facts. Facts are again categorized into three groups. So they say fully additive, semi-additive or non-additive. So here if you say I'm using a word measures instead of fact, but somewhere like if you read the books they may say fully additive facts, semi-additive facts or non-additive facts. So use this facts and measure word synonym to each other. That is not a problem. Now what the thing here is what is the fully additive measures? So some of the measurable data are which you can analyze using any one of the dimension directly. It means you don't have to depend on any specific dimension to make it meaningful for rest of the dimension. Like if I give one example, then it will be clear. Suppose if I'm dealing with sales quantity. So if I say that, okay, tell me what is the total quantity purchased by customer A. So this doesn't make any sense. Reason is, if a customer A has purchased 10 kg of rice, 10 liter of oil, and 10 meter of maybe rope. So you can't say like a 10 plus 10 plus 10, 30. Means you can't say like customer A has purchased total 30 units of 30. Because whatever product he has purchased, those products have a different unit. One is based on the kg, other is based on liter, and third is based on meter. And these are different units. They cannot be summed together. So such type of measures, we refer them as a semi-additive. Now question is why not non-additive? Reason is, if suppose if I say, give me the customer-wise, unit-wise total quantity, then sum is possible. Means customer, how many kg of the product he has purchased, we can sum. How many liter of the product he has purchased, we can sum. How many meter of the product he has purchased, we can sum. So when we attach unit dimension between quantity and other dimensions, then it becomes meaningful. But when we remove this unit dimension, then rest of the dimension becomes meaningless. So such type of measure which are meaningful to other dimensions because of one base dimension. So we refer them as a semi-additive because they can be applied for sum, means they can be added if the base dimension is there. But if the base dimension is removed, then sum is not possible or addition is not possible. So that we refer as a semi-additive. But some of the measures are like you can sum them or you can add them without thinking of any base dimension. For example, like we had amount base. So suppose if I ask, what is the total sales amount for customer A? We can say that, okay, customer A till today has purchased what? 10,000. Or if you want to know, what is the total sales amount from branch, maybe like XYZ. So it is like you don't have to worry about the product or anything. Simply you can sum up all the amount and say, till today branch A has generated $2 million. Like that you can. So whatever measures are there which are not dependent upon any specific dimension, we refer them as the fully additive because you can do the addition without thinking of any base dimension. And some of the measures are which are non-additive, means you can never say that you can apply sum or you can apply add. Like there are two specific measures. One is the rate and the second is a non-additive measure is like rate and percentage. Any value which is percentage based is non-additive. Like one example is which will make it very clear. Suppose if you go to one shop and purchase maybe one T-shirt, and I got 50% discount. Next day again I go and purchase one more T-shirt and got again 50% discount. I can't say that I got 50 plus 50, 100%. So that is not possible, because if you say 100%, it means you got it for free. But that is not the case. So whenever anything is based on percentage, you cannot sum it. That is why it is referred as a non-additive, because you cannot add 50 plus 50. Second is the rate. If it is like you purchase maybe one product for 10 rupees per unit one day, and the same product you purchase for 15 rupees on other day. So you cannot say like a total rate is 10 plus 15, 25 rupees. That has no meaning. Average is okay, means you can say 10 plus 15 by 2. So average is 12.5 rupees. That is meaningful. Our maximum rate is 15. That is meaningful. Minimum rate is 10. That is meaningful. But sum has no meaning. So rate also cannot be added, or it cannot be summed. So these two types of measures, or any other measure which is where you cannot apply the sum or you cannot apply addition, we refer as a non-additive. So why do we need to understand these three different categories? Whenever we are designing a cube for fully additive measure, we make sure that, okay, whatever dimensions we take, we check whether these dimensions are meaningful to this measure or not. If it is meaningful, keep it. If it is not meaningful, then we can remove it. But suppose if you are designing a semi-additive based measure cube or non-additive, then we have to make sure that what is the base dimension. And that base dimension must be attached with the fact table before you go for the rest of the dimension. So in case of fully additive measure based cube, you don't have to think about what is the base dimension, what is the non-base. But the time you go for semi and non-additive, then you have to think, means you need to identify what is the base dimension for this. So mostly it will be either a product or it may be like unit, these two are. But it differs from domain to domain or from business to business. So sometimes it is possible that you in a single fact table you combine all the three types of measures. Means you keep the quantity, rate, discount, percentage, everything in the single fact table. So in that case, you have to identify what is the base dimension and then rest of the dimensions keep them. Okay, so these are the types of measures. After that, we have there are different types of dimensions like role-playing dimensions. We have junk dimensions, degenerate dimensions, confirmed dimension, which we have already discussed. It means common dimension between the two cubes. Then inferred dimension, which is also referred as a delayed dimension, or we have a sunken dimension. So these are the like static dimensions. So there are about 7 or 8 different types of dimensions are there. And then comes the most important part, that is the slowly changing dimension. So slowly changing dimension basically is a type of dimension which defines how you capture the changes for the dimension data. It means, suppose I have a customer dimension table. So when we load the data in the customer dimension table very first time, all the data has come. Now after 1 month, customer has changed his address or maybe his city. So he was staying in Hyderabad, now he shifted to Mumbai. Table customer. Should I override this, means remove the Hyderabad and keep Mumbai, or should I keep Hyderabad and Mumbai both? So how to capture the changes at the dimension level within the dimension table, that is defined by the type 0, type 1, type 2, which is the most popular, and then 3 and 4. 4 and 6. So basically type 1 indicates that don't keep any history. Means if real life data is changed for dimension, in your dimension table also you change it. So remove the old data and keep only the latest. But when you say no history, this no history is against the rule of data warehouse, because data warehouse says keep historical data. And here you are saying I don't keep no history. So both are contrasting. Generally type 1 dimension is not used in the data. In a very rare case, it is used. Type 2 is where we keep the complete history. It means if a customer has changed his address, maybe changed his city 10 times in the last 5 years, all the 10 city reference should be available in the dimension table. So if anybody wants to analyze when the customer was in Hyderabad, how he was doing transaction with my bank, when he shifted to Mumbai, what was his transaction impact, its impact on the transaction, when he shifted to Delhi, how it has impacted. So bank people, they would like to analyze when the customers are changing their location, Does it impact their interaction with the bank or transaction with the bank? If yes, they will try to find out what is the reason. Maybe they find that when the customer is shifting to maybe some second tier city, most of the customers are stopping the transaction with my bank. What is the reason they find? In the tier 2, our branches are very less, and that is the reason people are not able to reach to the bank branch, so they will try to open an account in some other bank which is very near to them. So this might be one of the points for the management to increase the number of branches in a tier 2 city instead of just considering only tier 1 city. So when we have a history of changes for dimensions, then only we can study the impact. Why the transactions are increased because of these changes, the dimension level, or why it has decreased. So the best option is type 2. And then there is type 3, which is basically partial history. It means sometimes your client says, okay, don't give me all the changes, give me only current and the previous. It means if the customer has changed his address 10 times, so type 3 approach will say that keep the 10th address and the 9th, and the previous 8 address remove it. Don't keep in the database. This in dimension period. So sometimes your client may say that, okay, I don't want complete history because we do not analyze. So in that case, you have to go for type 3. So basically the best one is the type 2 dimension. And then there is a 4, 5 and 6, which is it has been introduced, means 4 and 6 are there, it has been introduced, but they are not used, it is rarely, mostly we avoid them. So when it comes to this dimension, type 2 is the best one, which is used very frequently, or we go for type 3. But one is not means advisable, or basically it is against the rule of data warehouse. And the type 0 is basically those dimensions which are like, once data is loaded in those dimensions, there is no change. Like for example, if you take, if I have one dimension table for month, so how many records will be in that dimension table? Only 12, January to December. And once you load those 12 records, you don't require to change. You don't have to change for entire life, because more than 12 months is not going to happen. Less than 12 months is not going to happen. So those 12 records will be there as it is. So such type of dimension where once data is loaded and they do not require any change either in the form of new records or updates, such dimension we refer as the type 0 dimension. It means static dimension or passive dimension. So here we discuss the same, like 0, 1, 2, 3, all these dimensions we discuss here. So this is the very basic of our dimension modeling. But when we go in like in our session, we discuss, and then each and everything we go in the practical way, like how we identify the dimensions. So I take a database like OLTP database of about 15-20 tables, and then we'll practice like from those tables how we identify what are the dimensions, what are the facts, and how we define the dimension table structure based on those 25-30 tables. So is it like we are going to have only 1 dimension, 4 dimension, 10 dimension, or if you get suppose 30 dimensions, do we keep all the 30 dimensions as a separate table, or we are going to club them? So it will be more practical oriented approach, not like just concept. So each and everything we have to see practically. Like when we talk about fact table, what is the fact table? How we identify? So if suppose I have 30 tables at the OLTP level, how we know that which table is having a data which can go in the fact? Means where is the measures which are numeric and they can be used in mathematical operations. So it is like once our theory concept is over, then we take one use case where we take around 15-20 table as a source or OLTP, and then whatever concept we have studied, step by step we apply and we see how we create a small data model. So which may involve 3-4 different cubes. Yeah, if you have any query or any questions, we can.
Hi Gopinath. Hello Gopinath sir. Hello Gopinath sir.
Yes,
If you have a question, you can ask directly to sir.
No, I don't have any.
Okay. Dinesh sir.
Yeah.
Yeah, thank you for giving a wonderful presentation, sir. My concerned person will inform you on the details. Okay.
Okay, sure.
Thank you.
Okay, thank you.